What if I told you that the AI making crucial decisions about your life might be as mysterious to its creators as it is to you? In this video, we're going to look at the black box of modern AI and uncover why explainability matters more now than ever. Stick around to discover why the trust but verify approach is becoming increasingly difficult and what it means for our future. I'm Evan Goldstein. I'm a licensed professional engineer and a data scientist. I'm making the AI Capitalist channel to help leaders like you penetrate the black box that's making more and more of the decisions that control our businesses and lives. Today's episode is going to get a little more technical than usual, but hopefully by the end, you're going to at least know what you don't know. So what do we mean by explainability? In short, explainability in machine learning is the idea that you could explain to a human user, not necessarily a technically savvy user, how a model is making its decisions. A decision tree is an example of an easily explainable or a white box sort of algorithm. Think of Zillow. Zillow is looking at different houses, gathering data about those houses, watching sales data, using that to make an estimate or a zestimate of houses that are outside of the known data set is a guessing value. It's just looking at the attributes. There are public records on houses, such as the number of bedrooms, square footage, acreage of the land, neighborhood, etc. And then comparing to the neighbors, it's going down this decision tree, size, bedroom, square footage, acreage size, etc., and coming to a value. Other kinds of decision trees can be more complex, and they can be considered gray box or even black box. Black box is increasingly difficult, leading to impossible for a human user to understand. A foundational lesson in any machine learning education was always that our relationship to models, which were usually boosted tree style models, should be at most trust but verify. When you train a model, don't take the initial predictions at face value, but spend some serious time kicking the tires. You have to test the model's behavior on very weird outliers. Even when they're unlikely to happen in the wild, they give you indications of how valid the model you're building is. You plot out the tree itself. And if it's shallow enough, you can use techniques like feature importance to determine whether the model is making inferences using features that correspond to your knowledge of the subject matter and logic. For example, if you were to look at a decision tree using the Zillow example, you might look at the tree and it's looking at different features, size, house color, location, etc. It's weighing these features and determining which are the most important and making an accurate decision. If it came out that the paint color of the front door was the most accurate predictor of a house's value, you're probably going to say that's wrong. That and know intuitively there's something off about the model. When modeling a physical phenomena, you can compare the model's behavior with what we know scientifically about how things work in the real world. You don't just trust her, you have to check it. It's trust but verify. Neural networks have become super popular. The big trade-off we face is that making neural network models explainable gets tricky. Their architecture complicates things. You can't look at it like a decision tree and figure out what it's using to get its answers. A good example of this is the husky versus wolf problem, where convolutional neural networks can sometimes miss the mark. A CNN was set up to tell the difference between pictures of huskies and wolves. When the researchers dug a little deeper into how the model was making its decisions, they stumbled on unexpected things. They found that the model wasn't actually looking at the animal itself. Instead, it was looking at the background colors of the pictures. There were more wolves than huskies in snowy settings during training. Every time the CNN saw a snowy scene, it just assumed that it was a wolf, even if there was no wolf to be seen. The model came up with its own way of figuring things out, and we never saw that coming. Instead of picking up on things like size, fur type, or face, things that we want it to be able to look at to differentiate the breeds, it was just looking at background hints from the pictures that have nothing to do with it. This shows how crucial it is to think about everything in the training data, as those factors can mess with machine learning models in ways that we didn't expect. The whole husky versus wolf example highlights how models can latch on to patterns we might overlook and make decisions based on irrelevant information. Understanding these behaviors is important for making AI systems more accurate and trustworthy. When it comes to checking how models perform, the old school question of whether a model thinks like we do in the real world just isn't as relevant anymore. Today's models are so complicated that they often do their own thing in ways that don't make sense to us at first glance. As we deal with models that make decisions we can't wrap our heads around, we're starting to rely less on the old school testing methods. Instead, it's about trying things out and learning from what happens. We shift our attention from figuring out how the model thinks to just checking out what it produces and then tweaking our inputs a little bit at a time based on what we see. These are called systematic experimental strategies. To figure out how these complex models work, researchers use hands-on experimental strategies that include testing different what-if scenarios. They play around with various inputs and watch how the outputs change, which helps us understand what the model's up to. Well, this method isn't exactly a walk in the park. It can be time-consuming and it requires a lot of computational power. And if you feel that you're gaining value from this episode, I would really appreciate it if you would push the like button. Pushing like lets me know that I'm making content that you want to see, and it helps spread that content to others. Together, we can help break this channel out of small YouTube channel hell. Thank you for your support. To really get a handle on these complicated methods, researchers test against a bunch of different counterfactuals. By mixing up the inputs and seeing how the outputs change, we can learn a lot about how the model works. But it's not all smooth sailing. This method can be a real pain because it takes a lot of time and computing power to run all the different variations of the model. Now, as we dive into the changing world of model testing, we need to switch up how we do things to keep up with these complicated models that aren't always easy to read. Old school tests just won't cut it anymore. By rolling with a trial and error approach, we can get the hang of how these models actually work, even if it feels like going in circles. So that classic way we used to wonder if a model is thinking like a human does is pretty much tossed out the window right now. Figuring out how a model is making decisions like we used to, forget it. Now we've got to roll with trial and error because there are some solid experimental strategies. I'm not saying that figuring out how neural networks tick is hopeless. Anthropic supports looking into how we can make sense of Claude by exploring what words, phrases, or images get those LLM gears turning. But the fact that they have to rely on trial and error shows that even the brilliant folks behind Anthropic's LLM don't fully know how it's coming up with its answers. To even start wrapping our heads around what neural networks are up to, we need to get real about randomness. Lots of neural networks love to shake things up, so you can't always expect them to spill out the same answer when you hit them with the same question. This is especially the case with generative AI models, which are set up to come out with different responses to the same prompt. It gives them more of a human or creative vibe, and you can spice things up or tone it down by playing around with something called the temperature. Think of it like a dial that changes how wild the outputs can be. Sometimes the models might go with a choice that's not the most obvious, but adds a fun twist to the answers you get. You can still mess around to figure out what the model's up to and why it's acting the way it is, but it definitely gets trickier. Instead of just fiddling with the input to see what happens, now you've got to think about all the randomness that's in the mix. When you notice a shift in the response, the big question is, was it the randomness acting up? Or was it something weird going on with the model itself? Why should we even bother figuring out how these models come up with their prediction? When we develop machine learning tools that directly affect decision-making and influence behaviors, we must embrace the responsibility for their outcomes. While human oversight does play a role where the predictions are sometimes reviewed before action is taken, the trend is shifting towards models operating independently, often without any validation. This is really concerning as the general public gains unprecedented access to highly complex machine learning models, usually without adequate understanding of their inner workings. When we create machine learning tools that influence decisions and change behavior, it's important to take responsibility for what happens because of them. We still check some things manually, like looking over predictions before we act. But more and more models are running solo without double checking. That's a bit scary, especially since everyday folks are using these complex models without really grasping how they work. Figuring out how a model works and why it does what it does is like doing your homework. Just like you'd want to check that a toy doesn't have dangerous stuff or that a machine won't break and hurt someone, getting to know the ins and outs of your machine learning model is super important. It can be tricky, but I'm all about making sure I'm not putting something out there that could mess things up for people. If you're building a model, it's up to you to really understand what it does and how it affects everyone. If you want to feel good about using your model, you've got to dig into how it comes up with its answers. Just know that you're in charge of what your model does and how it impacts folks and the world around us. If you caught my episode on the EU AI Act, it talks about needing human oversight on predictions, making sure our models don't make biased decisions based on protected traits like racial and gender categories. Even if you're not too worried about the ethics side of things, there's definitely a legal push for many of us to stay on the right track. When we're working with neural networks, there are still tools we can use to get a grip on how our model is making decisions. We've got to put in the time and effort to figure it out. Some people debate whether we need to fully grasp every detail of machine learning once we get past the basics. And honestly, they've got a point. But we can't ignore the fact that those choices come with hefty consequences and risks. In the best case scenario, your generative AI model might do exactly what you expect if you're keeping things nice and simple. In the worst case, you could end up in a total bind because the model reacts in ways you never thought it would. That could mean you look like a fool, your business might tank, or even worse, it could seriously hurt people. If you're okay with the idea that some things just won't make sense with your model, you're definitely rolling the dice on some big risks. And you can't just say, oh, that's just how it is when you built the thing, and then decided to put it out there and trust its predictions. A lot of tech companies, whether giants or startups, have accepted that generative AI will sometimes spit out results that are wrong, dangerous, or even biased. And they think that's a fair trade-off for the benefits they see. We know this because there are generative AI models out there that don't always follow the rules, and yet they've been released to the public. It really bugs me that the tech industry has just decided, without any serious conversation or thought, to expose everyone to those kinds of risks. But the cat's already out of the bag, so what's next? Chasing after explainable AI while trying to keep up with the rapid pace of generative AI sounds like a solid plan. The average person probably won't ever fully understand how these models work because they're just way too complex. That's why I think we should also dial in some risk management. It's super important to make sure that the folks behind these cutting-edge models, which affect our lives every day, are held accountable for what they create. Since the results are often a total mystery, we absolutely need some sort of framework to keep our community safe from the worst-case scenarios. That's not to say that we should be panicking over every little risk, but we also have to keep it real and acknowledge that risks are part of the game. The whole explainability issue with the latest AI tech makes it pretty tricky to figure out how risky machine learning can be. The smart move is to weigh those risks against the actual benefits we get from the models, and not just assume that the future updates will be magical, and make our decisions with that in mind.